All right, guys, in this section 6-9, we're looking at harmonic motion. And so harmonic motion is a special type of periodic motion where the restoring force on the moving object is directly proportional to the object's displacement, magnitude, and acts towards the object's equilibrium position. It results in an oscillation which, if uninhibited by friction or any other dissipation of energy, it continues indefinitely. All right? And so, like for example, a swinging pendulum is harmonic motion, possibly could be modeled also by waves in an ocean, or anything, or yo-yo, or anything that is oscillating in nature, right? And because of the periodic nature of harmonic motion and the fact that sine and cosine graphs are also periodic, it makes sine and cosine a perfect way to represent harmonic motion with an equation. And so that's what we're going to be looking at in this section. All right. Now, the sine and cosine equations are changed just a little bit with harmonic motion. And so one of the differences that you may notice is that the b is factored out here. Okay. And so the purpose of that and the benefit of that is once you factor this b out here, then this value right here of h, then that gives you your shift exactly. So it gives you your shift, your left or right phase shift, just by looking at this number. Because remember, phase shift in the other equation was c divided by b. Well, here we're factoring the b out, so you're taking the divided by b out of it so that this value is your phase shift. All right, so hopefully that makes sense. All right, and it's much easier to represent the phase shift by looking directly at this value factoring out the b, because of the fact that with harmonic motion, okay, the x-axis is going to be represented by time in seconds or minutes or whatever unit of measure, as opposed to being represented in terms of pi like it is with radians. And so when we're trying to match an equation up to the harmonic motion in the particular problem that we have, then it's much easier to adjust it by just saying, hey, if we move the sine equation over to the right by 2, by plugging in a 2 right here for this, or to the left by 2, or whatever it is, it's easier for us to write this equation. And then we also have a way also to calculate b, because b is still 2 pi over the period. All right, so it just makes it easier when it comes time to write the equation by trying to match the sine or cosine function up to the specific type of harmonic motion that we have in our problem. All right, and so that's kind of the main difference in the form of the equation. Let's see. As far as finding different parts of the equation, a still stands for amplitude, and it's max minus min divided by 2. The vertical shift is still d, and it's max plus min divided by 2. Let's see. We have a little different way to express the period here. It's 2 times the absolute value of the max minus the min. And of course, finding b is 2 pi divided by the period, so there's no change there. All right. So that's kind of the model for the equations, for the sine and cosine equations to represent harmonic motion. And here's some other things that we need to consider. All right. Basically, when we go to write the equations for harmonic motion modeled by sine and cosine, like I say, the thing that we're trying to get here, and the thing that we don't really have any specific equation here for, like we did in the last one, was to find the phase shift, right? So with harmonic motion, we find the phase shift by saying, okay, how much do I need to shift the graph of sine or cosine in order to make it match the harmonic motion that I have in this problem, right? And so the guide for doing that is kind of here. So sine typically reaches a maximum after the first quarter period. So by knowing that, if you've got a problem where the maximum comes first, then you can see that, okay, typically my sine is going to reach a maximum after the first quarter period. How much do I need to shift that left or right to make it match the specific problem that I have in this harmonic motion, right? And let's see, cosine typically reaches a maximum at the beginning of the period and the first minimum after half of the period, okay? So if the specific problem that I have starts with a maximum, comes to a maximum first, then I can look at the maximum of where cosine typically is and then say, okay, how much do I need to shift it over to the right to make it work, and create the appropriate equation to match it, okay? And if the minimum, if you have a problem where the minimum comes first, then you can say, okay, cosine typically has the first minimum after half the period, so how much do I need to shift that either to the left, probably to the left, or maybe to the right, to make that cosine equation match up. Now with sine typically reaches the maximum after the first quarter of a period, right? And if you have a problem where the harmonic motion that you're dealing with comes to a minimum first, we typically make that match up quickest by taking the sine and reflecting it through the x-axis. All right, and that's the point we're making right here. You can make the problem match sine or cosine when the first relative extrema does not match by reflecting through the x-axis, right? And that's typically when you're trying to create the sine equation, okay? And the first thing that you come to is a relative minimum, right? And I'll kind of show you what when we get into our specific problem, kind of how to do that and what we mean by that. All right, let's see. All right, so here's the problem that we're going to look at. So this one says, Mr. Keeping, disguised as Math Man, a costumed crime fighter, is swinging back and forth in front of the window to Miss Gibbons' class. All right, so at 3 seconds, he is at one end of his swing and 4 meters from the window. All right. At 7 seconds, he is at the other end of his swing and he's 20 meters from the window. All right. And we want to create the equations by matching the first extrema in the positive direction. Okay. So just to kind of get an idea of what's happening here. Okay. So this guy's swinging, toward the window and away from the window, on a rope. And so after 3 seconds, he's at his closest point to the window, which is 4 meters away, right? Okay. And at the farthest end, when he swings backward away from it, at 7 seconds, he's 20 meters away. And that information, of course, is shown on the graph that we have here with these 2 points that are listed for us. All right? So he's swinging back and forth. So the closest he gets to the window is 4 meters away. The furthest he gets from the window is 20 meters away. All right, so he's swinging back and forth. All right, so now we have some questions that we want to answer about this particular harmonic motion. Okay, and the first question that we come to is, what is the amplitude? Okay, what is the amplitude? Well, remember, the amplitude can be found by doing the max minus the min divided by 2. And so for the amplitude on this one, all right, the maximum value right here on the y value is 20. So we'll go 20 minus the minimum right there is at 4. And we want to divide that by 2. And so that'd be 16 divided by 2. And so the amplitude is at 8 meters. All right. So there's our amplitude. All right. We want the period next. So how do we calculate the period? Well, the period is going to be 2 times the absolute value of the max minus the min, and the time max minus the time min also. So keep that in mind. So with the period, we're going to go 2 times the absolute value. And so the time of this max is 7. And we'll go minus the time of this other max, which is 3. And so 7 minus 3 is 4 times 2 is 8. And so the period is 8 seconds. All right, so 8 seconds is the period. And just kind of relating this formula to the graph, trying to figure out what the period is. So remember, from here to here, right, whatever that distance is, which we found by subtracting 7 minus 3, remember, that's half of the period, right? Okay, so that's half of a full cycle, and then thus the multiplication times 2 here. All right? Let's see, what else do we need here? Now, the next question that we come to is one that says, okay, what sine equation represents this harmonic motion? Okay, so now we're going to try to develop the sine equation, okay, for this particular harmonic motion. Now, there's a couple of other things that we need to get, right? So we've got the amplitude and we've got the period, but we need to calculate the value of B, and we also need to calculate the value of D, and then we need to see what our phase shift is going to be to make it match up. All right, so let's calculate D. And so remember, D is going to be your vertical shift. And so that's max plus min divided by 2, so the average of the max and the min. And so here, my max value is 20, plus my minimum value is 4. I'm going to add those together and divide that by 2. And so that's going to make my vertical shift 12 meters. All right. And we also need to find the value for B. And of course, B can be found by 2 pi divided by the period. And of course, the period we already found to be 8 seconds, right? So that would be 2 pi divided by 8. And that's going to make B pi over 4. All right. So there's my B. So now I've got everything that I need to write the equation except what the phase shift is going to be. All right. So I can actually go ahead and start to write all the parts of my equation except for what the phase shift is going to be. All right. And so here's where these guidelines kind of come in. So remember, when we're looking at this, the first thing that we come to is a minimum. So remember, the quickest way to get the sine equation to match up when the first thing that you come to in your harmonic motion is a minimum is to see where the first maximum typically is, then reflect that, and then shift it to make it match. So here's what I mean by that. Okay. Remember, sine typically reaches a maximum after the first quarter period, right? It typically reaches a maximum after the first quarter period, okay? Well, the period is 8 seconds. So what's the first quarter period? So 8 divided by 4, or excuse me, 8 divided by, what am I trying to do? Yeah, 4 was right. 8 divided by 4 is 2. Okay, so sine typically is going to reach a maximum, okay, after 2 seconds. It's typically going to be reaching a maximum here. So that's where the maximum would normally be for sine. All right. Now, if I'm trying to get my sine curve to match this equation, okay, I really don't want to have a maximum come first. I would like for a minimum to come first. And so in order to make that happen, then when I'm going to start my equation, h of t, I need that to be equal to not just 8, but negative 8. And remember, by making that value of a negative, it is going to flip the equation through the y-axis, and then the shifts will happen. Okay, so really, if I start that off negative, then instead of at the first quarter period having a maximum, at the first quarter period, I'm going to now have a minimum. And then so now I can begin to write out the rest of my equation. So it'll be negative 8. We know this is the sine equation. All right. So then I come to my first set of parentheses, and we already found the B, because remember we're following now this pattern, right? So the B we've already found to be pi over 4. Oops. Which we did here, right? And so now we'll open another set of parentheses, and then this will be T. Okay, now here's where our phase shift comes in. Okay, so we've already flipped it through the x-axis and made our first minimum end up here. Now here's the question: what does my phase shift need to be in order to make this minimum hit here instead of here? Well, I need to shift it one space over to the right. So in order to shift it one space over to the right, I need to make this minus 1. All right, so I'll make this minus 1. And then that would shift it one space over to the right. All right. And because remember, this number now, whatever this value of h is going to directly be the amount of my phase shift. Why? Because we already factored the b out of these two numbers. Does that make sense? Because remember, like I had said earlier, remember in the previous lesson, our phase shift was c divided by b. Well, by factoring the b out, it makes this value the exact distance of my shift. So if I want to shift it over to the right one, I need to just subtract 1 from t inside of these parentheses. So like I say, that was the purpose of factoring the b out of here, so that it's easier for us to write our equation, because we just need to add or subtract whatever distance it is to make the minimum or maximum match up. Does that make sense? Okay. Let's see. So in order to finish it, it's not too difficult. I just need to add on my vertical shift to the end of it, plus 12. And then there's the equation. All right. Now, let's go ahead and write the other equation, and then we'll graph them to make sure that they match like they're supposed to. All right. So for the other equation, now the cosine equation, then it'll start off the same way. And so what we need to think about now with the cosine equation is, okay. Now with the cosine equation, okay, we typically don't have to flip it by making that amplitude negative, right? Or making that the value of a negative, because remember with cosine, it reaches a maximum at the beginning of the period. So right at the beginning there's a max. So if we've got a max, we'll just use that and shift it over. And the first minimum after half the period. So if it's a minimum that we're trying to match up, we don't have to flip it, right? We just need to go to that half period and then maybe bring it back to where the minimum should be. So with cosine, the maximum and the minimum are all within a half a period. And so there's really no need to flip it like you do with sine, because of the fact that it's so close together. Because with sine, it reaches a maximum after the first quarter of a period. Well, it reaches it would reach its first minimum after 3/4 of a period, right? And so it's much faster to just flip that maximum to reach the first minimum than it would be to go and get that minimum that's already 3/4 of a period over and shift it. Does that make sense? So that's why with sine, a lot of times to get that first minimum, we would flip it by putting negative at the beginning of the equation. But with sine, that's typically not necessary, because you've got a maximum and a minimum within half the period. All right? So what we're going to do now to try to match up this first minimum is say, okay, well, typically, where is the first minimum on cosine? The first minimum is after half the period. Okay, so let's go and see, where would half the period be? Well, the period is 8 seconds, right? So half of that would be at 4 seconds. So typically the first minimum in cosine is here anyway, which is close to the first minimum in this particular problem. And so all we've got to do is, when we come and do our phase shift, we just have to phase shift it to the left 1. So we'll reflect that in our equation. All right, so we know if the first minimum is typically here at half the period, then we know to make it match up to this curve, all we've got to do is we've got to shift it back to the left by 1. And like I say, we will reflect that when we start to write out our equation. All right, so like I say, no need to flip cosine like we did sine, because cosine has a maximum and a minimum within half the period. Okay, so if this was a maximum first, we would just shift the maximum. If it's a minimum first like it is here, we just shift the minimum the other way. And that's the quickest way to make it match up. All right, and so let's see. So now when we go to write it, okay, the amplitude is still the same. We'll keep it at 8. Remember, this is positive. 8 cosine, open. Our b is not going to change, so that's still the same. That's still pi over 4. We'll open, we'll go t. Now here's where our adjustment needs to be made. I need to now shift it over, phase shift it over to the left by 1. Well, how do I do that in the equation? So to make it shift over to the left by 1, then I'm going to need add 1 directly to the t. So I'll need to add 1 directly to the t. And remember, we already discussed the fact that I know this is just adding 1 to make it match up because we already factored out the b. All right, so this form for the harmonic motion makes it nice and easy to do your phase shift. And the plus 12 will still be the same. All right. So that's going to be your cosine equation to represent this harmonic motion. Okay, so just to kind of recap what we've done so far. Okay, you'll find the amplitude, you'll find the vertical shift, you'll find the period, you'll find the value of b, the same way just like how we normally do, and find those parts of the equation. And so the only part of the equation that you'll have to match up after that is you'll have to see, okay, typically where is the max or the min, right? Okay, and if it's a minimum that comes first with sine, okay, you're going to have to flip it by making it negative. And then after that, you're going to have to make sure you match it up as far as where does the phase shift need to go in order to make the curves match up. All right. Let me see. What else we got here? Okay, so before we move on, let's just graph these two and make sure that these are indeed the right equations that work for us. So in order to do that, we'll go back into our Desmos calculator here. And let's type it in. So the first one, -8, function is sine, and it's going to be pi over 4. Okay. We need another set of parentheses. We need an x, and we need -1, and we need a close. Whoops. We need a close parentheses. We need a close parentheses again, and we need a plus 12. Okay. And so in order to make sure that this is correct, why don't we just take a look at our points and see if these 2 points are the same as the ones that we got on the graph. So 3, 4, we know is correct. That was one of them. And this should be 720. And it is. So we know that that equation is correct. All right. Let's see here. And what about if I wanted to check the cosine one? Let's do that and make sure. So we'll go 8 cosine. We'll open. Whoops, open too many there. So again, we're at pi over 4. Pi over 4. And we'll open another set of parentheses and go x, what was it this time, plus 1. X plus 1, close it off, close it again, add 12. And as we see, it falls right on top of the other graph. So we do know that these are the 2 correct equations that we have come up with. Now there's one more question that is being asked here. It says, how far away is Mr. keeping away from the window at 10 seconds? Okay, so what we want to figure out is at 10 seconds, all right, at 10 seconds, how far away is he from the window, right? So I want to figure out how far he is away here at 10 seconds. Now that we've got the equations, that should be very easy to do. As a matter of fact, I'll just take this right up here and take the x out. because remember t is my time in seconds, and I'll just put a 10 in there for 10 seconds, and then we get 6.34, and let's just double check and make sure we get the same thing when we put 10 in here, and we do. So we know that that is going to be my correct answer. All right? So how far is he away from the window at 10 seconds? He is 6.34 meters away. All right? And so there you go. You will have the same type of questions that are asked on a harmonic motion problem now on your quiz.